Hey, hi. In this particular video, we'll be talking about techniques to check whether a number n is prime or not, to find out its divisors, factors, and so on, right? So let's start with the primality testing. So let's say given a number n, we need to find out whether it's prime or not, okay? So as we know, the prime numbers are 2, 3, 5, 7, 11, and so on, right? So that by definition, a prime p is called prime number if p is greater than or equal to 2, and there is no number between from 2 to p minus 1 which divides p, right? So that's the definition. By default, 1 is not taken as prime number, okay? And a number which is not prime is called composite. So we need to given a number and check that whether that is a prime or not. So one obvious way to do this would be to, let's say, just simulate this, that check from range 2 to p minus 1 and check whether there is any divisor available in that or not, right? So if there is a number n and we check from the range 2 to n minus 1 for all the numbers, let's say x, if x divides n or not, if we check this, if it divides then it's not a prime, or else like if no number divides then it's a prime, right? So if we run this particular type of algorithm, we get a order and technique for this. However, we would like to do better than this particular style. So let's look at how we can find out a number is prime or not better than order n. So what we can do is we can have a method is prime which given a number x can find out a number to be a prime or not in root n. Let's say there is a number n, okay? So let's say it's not a prime, so it must have some prime p1, prime p2, prime p3, and so on to the power some alpha 1, alpha 2, and alpha 3, right? So let's just think about one particular factor p1, and rest of the numbers we take all together and let's write that as d, okay? Now since this is not a prime, that means there should be one possible split between the numbers, right? There should be some p1 that divides this particular n, and from that we should be able to find out, okay, there is some prime that is dividing this n, and hence this n is not prime in itself. So what we can look into is, if there are two parts and their product is equal to n, then one of the part needs to be less than equal to root of n, right? If there are two parts and product of them is equal to n, then one of the part has to be less than equal to root of n. Now why is that? This is because if both of them are greater than root n, then a number greater than root n multiplied by a number greater than root n is equal to a number greater than n, which is not the case right here because we are equal to n. So this one of them will definitely be less than equal to root n, right? So if we loop from 2 to root of x, we will eventually find out some number which divides n, and if you are not finding any such number, that means n is a prime, okay? So that's the whole logic for this particular program, that we just like loop from 2 to root x. So rather than using square root of x, which gives you a floating or decimal number, we use this technique that, okay, we multiply I into I and check up to x, and we keep on incrementing. And as soon as we see that, okay, some number is dividing x, that means this x is not a prime, so we return not prime. Like 0 means we are checking is it a prime or not, so 0 means it's not prime, or else we return 1. Make sense? So this particular technique of finding whether a number is prime or not works in order root n, okay? So this particular technique is helpful when, let's say, the given input is up to 10 to the power 12 or generally up to 10 to the power 13. These kind of numbers you can find out whether it's a prime or not, okay? Now let's look at finding the divisors of a number n. So let's take a number, let's say 12. So 12 has 1, 2, 3 divides 12, 4 divides 12, 6 divides 12, and then 12 divides 12, right? So we basically have the like numbers d dividing n, and d lying in the range 1 to n. This particular set is the divisors of a number n. So we would like to find out the divisors of the number n. Now here again we have the opportunity that we can loop over from, let's say, from 1 to n, and for each of them just check whether it is dividing or not, and then accordingly we can just append it to some vector and find out all the divisors. But that would be a order n technique, right? We would like to do better than order n for finding divisors. Okay. Now we think about a particular logic over here, that we again resort to the same idea that we discussed just now, this p1 into d part. So let's suppose a number n is decomposed into two parts, some divisor 1 multiplied by divisor 2. Okay. Now let's chunk up all the divisors which happen to be appearing in the range 1 to root n. Okay. And from root n to root n plus 1 to n. Okay, these are the two chunks, and there would be some divisors in this chunk, some divisors in this chunk, but some of them might be empty, but that's it, right? In fact, they cannot be empty because 1 will obviously be there and n will always be there, so they are not non-empty. However, what I mean to say is, when we have this particular relation holding true, then for every divisor that occurs in this particular set, there is a divisor correspondingly available in this particular set. Okay. What I mean to say is, any number that you can find over in the range root n to root n plus 1 to n, for that particular number there is a one-to-one correspondence to a divisor which is in the range 1 to root n, because if that is a divisor, then we know that let's say there is a k number over here, so k divides n, so the number n by k has to be less than equal to root n, because k is greater than root n, right? So this particular number will lie in this. So there is a one-to-one correspondence between factors in this range, and we know that there are only, in this range there are only root n number of numbers present. Like from 1 to root n there are only root n distinct numbers, right? So a number n can have at most 2 into root n number of distinct divisors. Okay, make sense? So this is the whole observation that we have for divisors, that if for a particular number we talk about, a number can have at most 2 into root n, or you can say order root n number of divisors at first. Okay? So that is something that we are going to leverage out in this particular code. So let's have a look at what we are trying to do over here. So given an x, we want to find out the factors. So what we'll be doing is we'll be looping from 1 to root n. Okay, and let's say we find out some particular k which divides the number n. Okay, so we know that n by k is the one-to-one correspondent divisor in the range root n plus 1 to n, right? So for every number k that we find in the range 1 to root n, we know that there is another number in the range root n plus 1 to n which divides n. So that's what we'll be doing, that we'll be looping in the range 1 to root x. Okay, so x, we are doing up to x, and as soon as x mod 1, x mod I is equal to 0, we push I, and I square is not equal to n, so this means to be this needs to be x and this needs to be x. Okay, so when I square is not equal to x, that means I and n by I are two different numbers. That means we also need to insert x by I, right, in the solution space that we are creating. Make sense? So we just emplace x by I in the answer as well. Okay, so let's say if we are finding for some number 36, what we are doing eventually is we are looping from 1 2 3 4. Let's say for 4 we find out that okay, when we divide this by 4 we get 9, so for 4 we also appended 9, but then we went to 6, so 6 got appended over here, and then we saw that 6 into 6 is equal to n, so we don't append 6 again, right? So that's, in this way we can only get all the distinct divisors that we have, right? So we don't get 6 twice. Make sense? So this is how you can find out divisors for a particular number x in order root n, because we are only looping up to root n. Now let's talk about how do you factorize a number. So before we move into factorizing a number, let's talk about what factorization is. So for 12, let's say the factorization would be 2 into 2 into 3, right? For let's talk about 60, that would be 2 into 2 into 3 into 5. So rather than keeping these two separately, it sometimes helps to get like the prime and its count. So we would try to find out some sort of like this, that 2 comes twice, 3 comes once, 5 comes once, right? So this would be a much better representation of prime factorization. So we generally write prime factorization even on a notebook in such format, right? That n is equal to p1 to the power alpha 1, p2 to the power alpha 2, and so on. So it's natural to find out the prime factorization in the format p1 alpha 1, p2 alpha 2, and so on, right? So this is much better than like just finding out the factors in random order. Okay, so we would try to find out the prime factorization of a particular number, and for this again we would be using the same idea that okay, if a number has, if a number n has p1 to the power alpha 1, p2 to the power alpha 2, and so on. Like let's I'm currently writing I'm removing the alpha parts and I'm writing p1, p2, p3, which by that I mean to say that p1 can be equal to p2, okay, but they are distinct primes and all, okay. So I'm writing in this particular format. So what I claim to say is only one of these primes can be greater than equal to greater than root n, because as we know that their product is equal to n, and only one can be greater than root n, right? If there are two more than root n, then the product itself gets more than root n. So only one of them can be greater than equal to root n. So what we can do is we can like start in the range 1 to root n, and we can remove out all the numbers that we found, right? We can like keep on dividing on whichever prime factors we are finding in, and whatever we left with would be the number which is like greater than root n. Okay, so that's the idea that we'll be using in the code as well. So let's say we would like to find out in the format p1 comma alpha 1, right? So for that we'll be using a pair, and we'll be denoting pair as ii. Okay, so this is just like defining a data type ii, which will store two pairs. Okay, so now let's talk about having factors for a number x. So let's say you want to find out the prime factorization of the number x. So what we are doing is we are looping from 2 to root x, okay, and as soon as we find some I which divides x, what we are doing is we find out the number of times I appears in the prime factorization of x. Okay, so as long as x is divisible by I, we keep it dividing by I, and we keep incrementing the count. So we find out the alpha 1 for I, okay, and then that's saved in the count. So and we push the answers at the answer, we push back the pair I comma alpha 1, which is like this particular pair, right? I is the factor, I is the prime factor, and this. Now why is I going to be a prime? This is because let's say we are at 2, 3, 4. So before coming to 4 we would have reached 2, right? So if I is not a prime, that means there is some prime less than I which is dividing I, right? If I is not a prime, then there is some j before I which divides I, and j is a prime. But we, in this loop we would have reached j first, and we would have divided it by that. So that's why I has to be prime in this particular way. If you think about this, you will get to get a hang of it. So we can just place back this pair of I comma count in the answer. Okay. Now there is one particular part missing in this particular code. Can you think about what we are missing in this particular code? So this works fine for finding out the I comma counts. Now one thing that we discussed over here and which is missing in this particular logic. Yep. So over here we have not taken into the part where let's say one of them is like which is greater than root n, root x, right? So let's say we talk about let's say 14. Okay, so 14 has 2 and 7 as their prime factors, and when we loop from, so for 14 we would be looping only up to 9, only up to 3, because 3 square 9 is less than equal to 14, but 16 is greater than equal to 14, so it's not, is greater than 14, so we are not going to go to 4, so we are only going to loop up to 3, and in that case we would push 2 comma 1 in the vector, and x would remain as 7, but we would not go to like 3. Okay, so we'd only go to 2 now once this loop ends over here. So this 7 is still there in x, right? Now we noted that one of the factors can be greater than root n as well, so we need to just adjust that in the prime factorization, that if x is greater than 1 at the end of this particular loop, that means something is left out, and that is that one prime that we talked about, which is going to be greater than root n, okay, root x in this particular thing. So just take that prime separately, and that's your whole factorization of the numbers, right? Okay. So we discussed a lot of root n techniques. This will also be root n because we are looping only up to root n over here. Okay. So we discussed a lot of root n techniques that are frequently used in competitive programming, like finding out a number as prime or not using root n loops, finding out the divisors of number, which is root n. We also proved that okay, there can only be 2 into root n number of divisors for a number, and we talked about how you can factorize a number, which is sometimes helpful because we know that once you get the factorization as p1 to the power alpha 1, p1, p2 to the power alpha 2, and so on. With this factorization, we can calculate few properties of the numbers, like let's say how many divisors are there, how many, what would be the sum of divisors and all. Okay, so these things are relevant when once we find out the prime factorization of the number. So prime factorization plays a key role when we want to find out some property of the numbers of the number x. Okay, so that's all for this video. See you in the next one.